Today I'm going to talk about conservative forces and potential energy and conservation of energy. First problem here, we can look at potential energy stored in springs. And let's say we have a sack. Sack is placed on top of the springs. Um, uh, we have two really forms of energy in this case, potential energy stored in the gravitational field, gravitational potential energy, and energy stored in the springs. And if you were to remove some sacks from this, what would happen is the springs would elongate, and now it would move upward, and then you'd be storing more energy in or the energy would be converted from the potential energy in the spring to lifting the sack. Now, for the question that's asked here, you can think about it as 1/2 k s squared, which s is the deformation of the spring. And you could actually figure out how much energy by how much this thing is actually being compressed, right? We're given k. How much is it being compressed when you have 100 pounds being pressed on it, okay? Which is just, of course, be a fifth of a foot. So in this particular problem, young woman pulls a water balloon launcher back, stretching each elastic cords. And what if we wanted to estimate the maximum height and the maximum range of the water balloon when it's released from its current position? So what information would you need to know? Probably like the angle, right? Maybe the constants, the K values for the spring constants, or the elastic band or elastic cord constants would also give you that, potentially that give you that information, okay? And maybe something else related to the actual mass that the water balloon is carrying, or the water balloon, a mass of the water balloon. Here's another example. And in this case, you want to answer some questions about this roller coaster. And you want to know the velocity of the coaster at B and at C, okay? And knowing something like given the H. Okay. Also, you could actually find, if you didn't know H and maybe you wanted to find H and you knew something about the radii of these, or actually this is given, the radius of each of these is given. So you can also use that information to determine what height, which essentially is gives you initial potential energy. And when it gets down to here, in terms of its kinetic energy, what force will be applied upwards so that and relative to the weight of the passenger and the cart, that force acting down, if those two would cancel each other out, be zero. That's essentially what we're looking for here from both cases. And another concept we need to talk about here is the so-called idea of conservative forces. Okay, the idea is basically that work done in a closed path is not dependent upon its path. So in this case, the work done is only dependent upon its on its positions, right? Its initial position and final position. It's not in, it's independent of acceleration or velocity related to that. Something that's not conservative, if it has friction, right, then it would be dependent upon the path, right? The force you'd care about how far it's traveled. In that case, its overall distance traveled, let's say, or to get from one point to another. Okay, so you could define this conservative force. It makes use of a potential function. All right. So you could actually use partial differential calculus to come up with this. But in our case, for this course, what we're going to be looking at is just thinking about potential energy or conservative potential energy. So we don't really, when friction is not going to be one of the forces that we look at. In this case, what we're going to find is that our potential energy, our total energy, is just going to be equal to the gravitational energy in anything stored in springs. Okay, and that's really the problems we're going to be looking at. Okay, when relating, potential energy and work, what we're basically saying is potential energy is a measure of amount of work it'll do from changing position. Okay, so it's like the inverse, right? So you do work on a body if it's a conservative force, and basically that work, we use that work to convert over to energy or potential energy. Okay, if you do work compressing a spring, let's say, you're going to, whatever work you did to compress the spring essentially is going to give it the spring potential energy. Or if you had gravity, or if you lifted an object away from the surface of, let's say, the Earth, what you'll be doing is giving it gravitational energy, right? You do work to lift it, which gives it more gravitational energy. Okay, potential energy due to gravity. In this case, it's just the weight is equal to m times g, which is just the force, and then the distance. Okay, so here's our potential energy due to gravity, plus or minus, depending upon its direction. If it's going down or if it's going up. And it's going to be either we're losing potential energy or we're gaining potential energy relative to this point, let's say, or this line. And all it is, it's not dependent upon anything in the x direction. It's only independent. It's only dependent upon the y direction, okay, the vertical direction. And the point being is like if it's above the whatever we call the datum or original position, it's positive, and if it's negative, it's going down below it. The other type of potential energy we're going to look at is force of elastic spring. Okay, so potential energy is stored in a spring, and in this case, it really doesn't matter if it's a stretch or a compression of a spring, right? It's not positive. It's always positive in both cases, okay, in terms of that energy, right? That's the thing to pay attention to. And of course, this is the formula we had found previously, right? Just 1/2 k times s, and s squared, sorry. And s is the amount of deflection or deformation, I should say, deformation of that spring. And here it is, okay? Yeah, so here's the result of integration. And one of the things we say about this thing is that it's a linear spring, okay? Or at least in the linear range of the spring. And as we said before, it always yields positive energy. Okay. This leads us to the idea of conservation of energy, all right? So when it's acted on, systems acted on by so-called conservative forces, it's the energy is conserved, okay? So what this basically means is that, whatever this would be like our kinetic energy in one state plus our potential energy, sometime later we have new potential energy, let's say this object or particle is moving, this particle is moving, it has been acted by with some forces, and a little while later it has some kinetic energy and some other potential energy associated with. But the key point here is it's constant, okay? The understanding that there's no friction in the system, right? So it's not being, it's all conserved. So we keep the same in terms of the system or the particle that we're looking at. It has the same initial energy as the final energy, or in state one is the same as it is in state two, okay? The other point, of course, is here's the kinetic energy, 1/2 mv squared. Okay, so here's an example. So we have a collar. It has initial velocity at A. It's connected to a spring. And, we can make the assumption that this is, frictionless. That's just sliding along here. And we want to find the velocity at B, okay? So if you think about kind of what's happening, we have some initial kinetic energy associated with it. um, at point A, and some potential energy associated at point A. And then at point B, we have the same thing. We have some initial, we have some, so at point B, we have some kinetic energy and some potential energy associated with it. Okay. And if you think about it, what are the energies that we need to be concerned with? Well, we have energy stored in the spring. We have some um, gravitational energy due to its position. And we have some kinetic energy due to its initial velocity. Okay. So those are the things we need. So we'll have essentially three terms on each side of the equation, right? Because what are we saying? We're saying initially, whatever the initial energy is of this collar is going to equal to whatever the final energy of this collar is. Okay, so here's our system diagram. So what's going to happen? So our collar's here at some position, and you need to figure out like from this point up or relative to this point, the position vertically for the gravitational energy associated with it. And we need to know how much the spring is stretched, okay, at the final position. And what we recognize here, that it has an unstretched length of 0.2. So first, when it's up in this position, you can see that, there's actually some energy stored in the spring here. So there's some kinetic energy initially, some potential energy stored in the gravitational field or gravitational energy. And there's also some energy due to the compression of the spring stored there. So like I said, we're going to have three terms on each side of the equation. Okay. So we can look at it. We have the two potential energies. We're going to have here as our energy stored in the spring. This is at point B. So we're going to have gravitational energy, which is 0.4 from, and that's going to be negative because the 0.4 is essentially from this position all the way up to here, point A. Okay. So we could say that this is our datum point, at this level, and then it becomes negative. Okay, so we really can use this as our reference as opposed to down here because we're not given any information for down here. If we were, we could, but in this case we are not. Okay, so we have gravitational energy, and that's this term right here. It's minus 4 times 9.48 times 0.4, which is the distance. Okay, the other one is the spring. So one of the things we need to figure out here is that this is 0.3, this is 0.4, this side, and then this is a 3, 4, 5 triangle. So then this becomes 0.5. So it's two positions. First, in its unstretched form, it's going to be it's 0.2. So here's our unstretched. It's 0.2. And 0.5 is our final stretched length of our spring stretched. So here's the difference between the two. So this represents essentially the spring energy stored in the spring. And here's the gravitational energy. And the last part is the kinetic energy, right? We don't need to know what this is at this point yet. Okay, so our initial, since we considered this to be like our 0 point and reference, we made this 0. There's going to be no gravitational energy associated with position A. There's only going to be energy stored in the spring and kinetic energy. Okay, so that's a little bit different. Depends upon where you actually define your reference point. This is a good reference point. You could have made it B. It really doesn't matter. But A is a good reference point to start with because then we're saying essentially that we have 0 gravitational energy. Okay, so here's the two terms that make up the left-hand side of the equation, not 3. The other one's 0, so you only have 2. Okay. Okay. So now you put everything together. Essentially, you're saying that everything these are all the terms that we had in the position B. These are all the components of energy in position B. And here's the components in position A. Okay. Set them equal, then you can just go ahead and solve for B. Okay. It's a squared term, so you're going to take the positive one in this case. And your final result would be 1.96 meters per second. Okay. So really it's a matter of making sure you included all the energies that are associated with it. Like I said, if you make this the datum point or this the datum point, then it cancels out one of the terms, which is good. In fact, in this case, they really didn't give you any other information, so you don't know how far down this is, so you couldn't even solve for that anyways in the first place. Okay, so in this problem, this is a roller coaster problem. We have an 800 kilogram roller coaster is released from rest, and you want to find the minimum height h. So a car travels inside a loop at B without leaving the track. Okay, so without essentially falling down. Okay, and then also finding the velocity at point C. Okay. Okay, just a note down here how you can go about solving this particular problem. Okay, so this is the same thing. This is a conservation of energy problem, conservative forces. And we're going to have, any initial kinetic energy plus its initial potential energy is equal to its kinetic energy plus its potential energy at another point. In this case, we'll start off with point B. All right. So first part here is that we have some initial kinetic energy, which, if you go back to the problem statement, it's released from rest, so it has no kinetic energy, and that's where we get our 0. And the potential energy, in this case, it really depends upon where you're actually defining your 0 point. At this point, we define this as our datum. So this is our starting point here. And of course, there's going to be, because of that, we define the initial potential energy as 0. Okay. So we're going to have a negative term here. So now we're going to have some kinetic energy when it gets to point B. And we're going to have some potential energy. And the way this is written, and you could write it a little bit differently if you wanted to. You could have actually, if you wanted to write it in terms of this minus this point, you could have done that. But what we'll do here is that this essentially represents our position here at point B. So the way this one will be written is we know relative to point C, where B is, that's defined as 20 meters. That's defined as 20 meters. So we're going to write it as h, which is the whole height, minus 20, is going to give us the distance from A to B vertically. Okay, and it's a negative. So in this case, it's a negative because it's a negative potential energy or negative gravitational energy because we define this as our datum point. Okay, so you have your one equation here, and you'll see you'll have two unknowns. Okay, well, there's one more thing we need to apply, and that's our force, our equation of motion. And what do we care about? Force in the normal direction. Why? Because what we want to do is we want to determine the force in the normal direction, which is the force basically pushing out this in the opposite direction due to the motion of this the roller coaster, is going to be equal to the mass essentially, and the mass of the people plus the roller coaster going down. Okay, so we can make this substitution in here into this equation. You'll notice that mass times acceleration in normal direction, the mass shows up on both sides of the equation, right? So because this is the gravitational force going down, and the other force over here, is the force going in the other direction. Okay, so the summation of the forces is basically going to be a is going to be the normal force in one direction going up and gravitational force going down, and that's what this is. Okay. All right. So you can use this equation, our equation of motion, to solve for VB. Then you could take that VB, the velocity at point B, and substitute back into our conservation of energy equation and solve for our unknown. So this is all zero on this side of the equation. Solve for our unknown h, and h comes out to be 23.75. Okay, so this is our original equation. So what we recognized right off the bat was, of course, we had one equation. Our first equation, we had two unknowns. So we needed to come up with our second equation, which was equation of motion, because we were given that definition where we wanted to find that minimum velocity. And here's actually the diagram, free body diagram for that. Okay. Okay. Going back to it. Okay. And then, of course, to find the velocity at c, of course, we can apply our conservation of energy equation again, where, of course, no energy is being lost in this, or none of it's being converted to like heat or anything else. So we have whatever initial energy we had, it's going to equal the final energy we had. So now we have a new point here, which we recognize. We know this is 3.75 now, or sorry, not even 3.75. We have 23.75. This is 3.75, so it's 23.75 for the distance from A down to C. We substitute in our equation here and for that distance, and then we can solve for VC, which in this case comes out to be 21.6. Okay, for this particular problem, we it's kind of like I guess a pinball machine, right? So you can pull back the spring and use it to strike the ball. Okay, so we're given some information here. You pull back the spring, you basically have stored energy in the spring, then you release it, and then all that energy is converted to motion for the ball to travel up on this semicircular curved track. Okay. So what are we doing? We're going to look for the speed of the ball and the normal reaction, or the normal force, when the ball's at 60 degrees, or the angle theta is at 60 degrees. Okay. So what we can do, of course, this looks like a similar problem to what we had previously done, and we're going to use the same things, of course, except we need to look at this position a little bit differently. So we need to use conservation of energy and then the equation of motion. Okay, we'll do that. Okay. Okay, so here's the conservation of energy equation. And what we could do is we could do these terms individually. So first thing, we have some initial kinetic energy associated with the ball. Well, initially it starts off at 0. And then we have some potential energy. And since we define our data point as at point A, this is our vertical position, we have nothing, no gravitational energy. And here's the actual energy stored in the spring. Okay, so no kinetic energy, no gravitational energy, only energy stored in the spring. So that's the left-hand side of the equation. Then the right-hand side of the equation, just a small error I noticed here. This should be VB squared. This is not, should not be 0. Okay, this is a mistake. I'll have to correct that on the slides. Okay, so TB should be 0.5, 0.3 VB squared. Okay, and then its potential energy. Here's my weight, and then the author chose to write it a little bit differently, but basically you're trying to find from this point up how far it is, which is basically 1.5, so it's 1 times 1. So it's 1.5 minus 1.5 times the cosine of 60. Okay. So essentially you're subtracting out this component from 1.5. Okay. And that'll give you the distance from here vertically to B. Okay. So then you can go through and solve this equation, right? Just make that note. VB, this is VB squared right here. Okay. And you could solve for it, and there you have your end result, 5.94. Okay. The second part requires that you come up with a free body diagram and the kinetic diagram. Okay. And this is what you're going to have. So you have a normal force when you're at, your angle 60 degrees, and you have the weight acting the other direction, right? So these are the forces acting on the ball. And then here is the kinetic diagram, which you're going to have a normal acceleration and you have a tangential acceleration, okay? And for us, of course, in this equation, what do we care about? We care about the normal acceleration, okay? So we care about the force basically acting in that direction. So force in the normal direction basically is going to equal to the mass times acceleration in the normal direction. And that, of course, is just going to be, this is our acceleration. When we had talked about kinematics using normal and tangential components, this is our normal acceleration. Okay, so for curvilinear motion, this is essentially what we've done previously. Okay, so when we go and define that, so here's our normal, and here's our gravitational force, right, which is acting in the straight down. But in case our normal one is, this is our axis, right? Our new axis is, this is our tangential and this is our normal. So now the weight, the part that we care about, is this part over here, right? And that's what this is. And it's the cosine because it's the adjacent side. So it's 0.3 times 9.8, which is the weight. And here is the angle. So this gives me, this all is the side, this side of the weight, right? Or this component of the weight, right? Then you can substitute in for VB, which we previously found, and rho was given 1.5. That was our radius curvature, which is 1.5 meters, which was already given here. And then we can go and solve for our normal force, N. And that's that. And that's the end of what we're going to cover in chapter 14.